All right. Let's please get into it. We're going to continue. So we talked about specific heat for solids and liquids. And we found the following. We mentioned the following. For solids and liquids, we had, let's say when the temperature is changing, we said when you add heat, it causes the temperature to change. But the change is proportional to, I'm sorry, not the change. The heat added is proportional to the temperature change. It also has to do with how much of the material that you have, right? If you add 10 joules of heat to 1 kilogram of water versus 10 joules of heat to 100 kilograms of water, 10 joules of heat to 1 kilogram would be much more effective than to 100 kilograms. And then there is the specific for that solid or liquid. So for gases, on the other hand, when you add heat, you can change their volume. So you can add heat at different conditions. So let's talk about gases. This may be a review. So for gases, we're going to add heat and ask, what's the temperature change when you do that? So you can hold the volume constant. You can You can also hold the pressure constant. You can hold the pressure constant. Let's talk about constant volume first. So here is the volume. Always a gas inside a cylinder with a piston here. And the piston is locked. This is constant volume, so the piston is locked. It cannot go up or down. Since the piston is locked, it means the volume is constant, and therefore the work done is how much? Zero. So by the first law, we have delta, the change in thermal energy, which is the work plus Q, the work done on the gas plus Q, but W is zero, so it's just Q. Okay. So at constant volume, when you add heat, all of that heat goes into changing the thermal energy because there is no work being done. So the temperature change, every bit of every joule that you added will go into changing the temperature of the gas. Now, how does it work? We'll imitate this. For a gas, we don't like to talk about mass, we like to talk about the number of moles. So for a gas, we can write Q is equal to the number of moles times the specific heat times the change in temperature. But because we changed the temperature at constant volume, we're going to call this CV. So this is the number of moles. I'll just say it. I will not write it. I'll just say number of moles is N. CV is the specific heat at constant volume. Right. And then delta T is the change in temperature. And this is the heat that you have. Let's look at the other one, which is constant pressure. So what's the difference? Let's see. Pressure. Here's the cylinder again. Gas is trapped here. And you're going to add heat. Just like you added heat here. And to add heat, you would like the pressure to remain constant, so the pressure inside and outside will be the same, and so the piston here is free to move. So when you add heat, what happens to the piston? It will, the gas will expand, will go up, the volume will increase in order for the pressure to remain constant. The piston used to be here, and maybe now it's here after you added some heat. So the volume became larger. Right? But the pressure is held constant. So in this case, let's write down the change in thermal energy. The change in thermal energy is equal to the work done on the gas plus Q. Now, look at this. When you add the heat, the gas expanded. So the work done on the gas, is that a positive quantity or a negative quantity? It's negative because it expanded, and so the gas did positive work, but the work done on the gas is negative. So look at the heat that you added. Q, that's the heat that you added, minus something is equal to the change in thermal energy. So part of the heat that you added went into doing work against the environment. And so not all the joules of heat that you added went into changing the thermal energy, rather some of them went into expanding the gas. That leads us to write the following. Q, very similar to this, it's going to be mc delta T, but because the pressure was constant, this specific heat is going to be different from this one. Now let's try to reflect on this Cp and Cv. To cause the same delta T, let's say I raise the temperature here by 10 degrees Celsius, and I raise the temperature here by 10 degrees Celsius, the number of joules that I have added here in order to achieve a 10 degrees Celsius change in temperature versus the number of joules I had to put here, they're going to be different. In here, every joule I added went into raising the temperature. In here, some of the joules I added went into raising the temperatures, others went into doing work. And so I have to add even more than here. It's more difficult to raise the temperature of the gas at constant pressure than it is to raise it at constant volume. This means if something is harder to raise its temperature, it means it has a higher specific heat. So the specific heat at constant pressure is larger than the specific heat at constant volume. So what I'm saying is Cp would be larger than Cv. Would be larger than Cv. So let me write down some side work here, some things that we will show. So the first is qualitatively Cp is greater than Cv. More quantitatively, we will show this in a little bit. We will show that Cp is equal to Cv plus a little bit more, and that little bit more is R. And R here is the ideal gas constant, 8.314 joules per mole per Kelvin. That's the ideal gas constant. Okay. We will also see that the change in, we'll also see that for what are those Cp and Cv for the different gases, we will see that for monatomic, we're going to have Cv, it's going to be 3/2 R, which means if Cv is 3/2 R, Cv plus R is Cp, so 3/2 R plus another R, it'll be 5/2 R. We're going to see those. So 5/2 R. Cp is 5/2 R. For diatomic, Cv would be 5/2 R, and therefore Cp is equal to Cv plus R, and so that's going to be 7/2 times R. Okay. So we see that. And then people like to define the following quantity, because we talk about adiabatic, people like to define the following quantity. Gamma, it's the ratio of Cp to Cv. Is gamma more than 1 or less than 1 or equal to 1, or it depends? It's greater, because Cp is greater than Cv, so you get greater than 1. So this is going to always be greater than 1. Now, gamma for monatomic. For monatomic, it's going to be Cp over Cv, so 5/2 R divided by 3/2 R is going to be 5/3, right? Which is going to be a number, 5/3. For gamma for diatomic, it's going to be 7/2 over 5/2. The R's cancel, so you get 7/5, which is about 1.4. We're going to do this actually in the lab. We're going to have a bubble of air. We're going to crush it quickly, and then we calculate gamma. before I go to the example, before I go to the more theory, let's do the following example. I'm going to ask you intuitively what's going on, and then we'll solve it quantitatively. So consider a diatomic gas. And the diatomic gas is initially at 20 degrees. So we have 3 moles of diatomic gas. So 3 moles of diatomic gas. ID gas. At 20 degrees Celsius. We're going to do the following to it. Here's the PV diagram. Gas is here. This is state 1. What we're going to do to the gas, we're going to add 600 joules. So we're going to, from 1 to 2, it's going to be isobaric. We're going to add 600 joules of heat at constant pressure. Okay? And then, so this happens. We're going to add 600 joules of heat at constant pressure. Constant pressure means we're going to follow a horizontal line. So are we going to go to the right or to the left? We're going to add heat, so we're going to increase the temperature, so it's going to go to the right. So this is 2. We're going to do this. And then, that's from 1 to 2. From 2 to 3, we're going to remove 600 joules of heat at constant volume. So remove 600 joules of heat. So are we going to, and it's going to be a constant volume. So it's going to follow a vertical line, right? Constant volume. So are we going to go down? Yes. Now, let me ask from your intuition on what we know about CP and CP. We injected 600 joules of heat at constant pressure, and then we removed 600 joules of heat at constant volume. Is the final temperature going to be 20 degrees Celsius, right? We started at 20. And then we added 600 joules in a special way, and then we removed 600 joules in another special way. So is the final temperature going to be 20, more than 20, or less than 20?
Yes.
Because? Heard less? Huh? With somewhere. Okay. It's going to be less than 20. Okay. Like that?
That with the ratio of CP going to NCP, and all you have change.
Okay. Hold on to that thought also. Yeah, I like it. Anyone else? Maybe a third person? There's almost a consensus. Everybody said it would be less than 20. The answer is it would be less than 20. The math would tell us so. So yeah, when you add heat at constant pressure, you do increase the temperature. But when you remove it at constant volume, the decrease would be even more because the CV is less than CP. It's easier to lower or raise the temperature at constant volume. The effect would be more with constant volume. But let's, that's the intuition or the physics. Let's let the math do its job. So, how are we going to solve this?
So question asking us what's the final temperature?
Yes, what's the final temperature? Sorry, I didn't state it. Yeah. So find the P final. I guess I was just saying, find P final. The temperature at 3. Yeah. Then
We could just find the change in temperature for
okay. So from 1 to 2, let me put here Q from 1 to 2 is going to be what? Equal to and CP delta B. Good. And the Q here is how much? 600. Good. Equals to the number of moles is 3. What should I put for CP?
7 over 2.
Huh? 7 over 2, you said? Yeah,
Yeah.
7. It's diatomic, and it's 7 over 2 R, right? Yes. 7 over 2 R. And what's R again?
8.314.
8.314. So I would just write R for that. When you plug in, put in those numbers. Change in temperature. It will be the temperature at 2 minus the temperature at 1, right? Temperature at 2 minus the temperature at 1. Should I put the temperature in Kelvin or degrees Celsius, or maybe it doesn't matter? It's a difference in temperature, it does not matter. So if I write degrees Celsius here, if I put 20, this temperature when I calculate it is going to be in degrees Celsius. If I put 293, which is in Kelvin, this temperature here will be in Kelvin. So it's up to us and up to you. So just make sure you're comfortable with this, okay? Make sure you understand. So T2 will simply be, I'm going to just read out the number, 26.8. So the temperature did rise. It was 20, it's 26.8. Next, we're going to remove 600 joules at constant volume. When you remove 600 joules at constant volume, it will not decrease by 6.8, right? It rose by 6.8 now, but it will drop by more than 6.8 because there is no work being done. All of the energy will just be taken away from the temperature, from the thermal energy. So for the Q from 2 to 3, it's going to be N C what? B, yes. Delta T. And what should I put for Q? Yeah, because we removed, so it should be minus. Yes, we removed 600 joules. So minus 600. N is again 3. CV is 5 halves, yeah, R. And then delta T, it's T3 minus T2. And what's T2? 26. And so T3 is going to be 17.3. 17.3 degrees Celsius. Okay. Yes.
So, in the first part, we don't have to remove the work because that's done by the ratio of the 7 over 2. Like we don't have to do NCAT minus the work done.
No, this relation is
Yeah.
is
Okay.
for the heat.
Got it.
And CP. Yeah. We can find the work if we want to find the thermal energy. So, yeah. Let's go to, now the next one is going to again be a review from yesterday for some of you. So relationship between CP and CB, and I think it's worth saying again. So CP and CB, relating CP and CB. And that's where we get that CP is equal to CB plus R. And if you recall, or here's the idea. Here's B, here's P. And we said, draw two isotherms. Let's say this one here is the temperature, let's say it's 300 Kelvin. Okay? Just to give a concrete example. This one is 300 Kelvin. And this one here is going to be more than 300 or less? More. More. So this is higher temperature. Let's say it's 400 Kelvin, okay? So this is the lower, that's the higher. And we're going to take the following processes. I'm going to use different colors. Here are the processes. Here's the initial. This is initial. And I want to go vertical. This is the final. This process here, let's call it process A. And I'm going to write down the change in thermal energy in process A. And I'm going to write down process B. Process B is going to, process A, by the way, is isochoric, right?
Yeah.
Constant volume. Process B is supposed to be horizontal, so it's going to be isobaric. Here's process B. It's going to be isobaric. Now, what do you notice about the initial and final temperatures in both processes, A and B? Same or different? They're the same. So the change in temperature for both process A and B, it's the same change in temperature. The thermal energy, the change in thermal energy depends only on the change in temperature. Therefore, what do you think, what's the relationship between the change in thermal energy between A and B?
Equal.
They're the same. Thermal. Now, I'm going to draw two more just to drive the point. Let's say I have process C. Let's say process C goes like this. Here's process C. What's the change? Is the change in thermal energy in process C going to be the same as A or different?
Same.
The same, because the change in temperature is the same. And then let's say this more arbitrary process, process D, that goes like the wiggling, like this. So the change in thermal energy through that process is also the same. As long as we don't care what happened in between, only cares, thermal energy cares about what is the temperature at. Okay? So the change in temperature is the same, the change in thermal energy is going to be the same. So that is that. That's the first one. Next, we're going to look at the two processes, at each process different, and then we're going to set them equal, and then we see what happens. So for process A, change in thermal energy is equal to work done on the gas plus Q, but the work done is what? Process A? 0, right? Because it's isobaric. Okay? Now, how about the heat added in process 1? Process A. The heat that you added. And CV delta T. Good. Yes. So delta E thermal. Good. In process A, just N CV delta T. So Q was eliminated by that. Then we write for process B. We're interested in A and B, but not C and D, because A is isochoric, B is isobaric, so they will give us a relationship between P and V. So let's look at the change in thermal energy in process B. It's going to be the work done on the gas plus Q. Here, the work done on the gas is minus P times delta T, because it's isobaric. And then Q is what? N C P delta T. And then now comes this word we did earlier. Delta thermal of B is the same as A, but A is this. And we write this one. T. And it's also good to note that P delta V is the same as delta P V, because P is constant, you can just pull it out of the delta, and then PV is equal to NRT, so we have delta NRT, and since NR are constants, so we have NR and then delta T, and so we're going to replace that by NR delta T, and be done. Just have to cancel the n's and the delta t's. So you have Cp minus R is equal to Cv, therefore Cp is equal to Cv plus R. So we have shown this relationship between them. And so from now on, we can just use that. So Cp is always larger than Cv, and it's equal to Cv plus R. Then, the next example is going to be on the adiabatic process. But in order to do that, I'm going to cover how the pressure and volume relate to each other in an adiabatic process. So we have the ideal gas law, but the adiabatic process puts more restriction because it's a specific process. For adiabatic, just like when you have isothermal, you have an extra piece of information, delta T is 0. You have isobaric, extra piece of information, delta P is 0. Isochoric, delta V is 0. In here you have one more piece of information. What do we know?
Q is 0.
Q is 0. So Q is 0. So we're going to, so that's an extra piece of information that we want to take advantage of, and we get an equation that we didn't know earlier. So we're going to, the idea is to start with the differential form, to write down the ideal gas law, not the ideal gas law, the first law in differential form. So I have dE thermal is equal to the work done, that's minus P dV plus Q, plus dQ, but there is no Q, so that's 0, part is 0. Now, the thermal energy, regardless of the process, it only cares about the change in temperature. And I think I said this, the thermal energy, let me write it here, delta E thermal, it's always NCP delta T, regardless of the process. Okay? This is regardless of the process. So dE thermal is going to be NCV dt, and this is minus P dV. All right. I want to relate P to V, but I have T. So what I will do first, I will eliminate P with the differential dt, and then integrate, and then finally I'll get the relation between T and V, and then we can use the ideal gas law one more time to get P into the picture. That's the idea. It sounds like a lengthy process, but it's really not. So we're going to start here. So I have N CV dt is equal to minus P dV. So the pressure by the ideal gas law is nRT over V. N cancels, and we can divide. So we get dt over P is equal to minus R over CV, and then I have dt over V. The next step is to integrate, right? Integrate from the initial to the final. So from our initial volume to our final volume, and from our initial temperature to our final temperature. And when you integrate 1 over, you get a natural log, and then you subtract them, and so it becomes T final, natural log of T final over T initial. So we had ln of T final over T initial, like so. And then on the right-hand side, we got minus R over Cp, and then ln of T final over T initial after integrating. We did this integral before, so that's why I'm just, we're familiar with it, so there is no reason to do too many steps. So then I have ln of T final over T initial. Notice that if you have, I mentioned this property of flux, you have ln of x to the y is the same as y times ln of x. So this would be the exponent. So this minus r over cv will go here and become the exponent. Okay? Will become the exponent. But it's a negative exponent. So I would have ln of, when you have a negative exponent and you want to make it positive, just take the reciprocal. So it's going to be this. V initial over V final to the power r over cv. Okay? I guess I have to go to the next word. So if you do e to both sides, you will just have T final over T initial equals to V initial over V final to that power. So I would have this T final over T initial is equal to V initial to the power R over CV, and then V final to the power R over CV. And cross multiply and you get T final V final to the power R over CV equals to T initial V initial to the power R over CV. And then use the Adiabatic law. T final is T final V final over NR. So you have T final V final over NR, and then this is V to the 1, right? And then you get V final to the R over CV, and then on the right side the same thing but with the initial. So P initial, V initial over NR, and then V initial R over CV. Okay? And NR cancels. And then here you would have V final to the first power times V final to the R over CV, so the power is n. So you just have this. V final, V final to what power? Well, it would be to the power 1 plus R over CV. And 1 plus R over CV becomes CV plus R divided by CV. CV plus R is what? CP. And so you have CP over CV. Okay? CP over CV. So I skipped a step. And what is the definition of CP over CV? It's called gamma. Okay, so that's what it is. Down here. And so it's P initial, gamma. And this, another way to write it is saying P V to the gamma is constant. This is for an adiabatic process. You cannot use it for isothermal, you cannot use it for isochoric, you cannot use it, you can only use it for adiabatic. Okay. This one is specifically for this adiabatic process. Okay. Before I proceed, we'll do an example. Actually, I should ask, does anyone have a question on any of this stuff?
Can you just explain how the exponent of 1 plus r is equal to v?
Yeah, so it becomes, when you combine them, it becomes 1 plus r over cv. And so when you make yeah, so you have this. You have v to the 1 plus r over cv, right? And that becomes v to the cv and then CV plus R. After we make a common denominator with the pip. Yeah, and then CV plus R is C. Which is that?
What is specific heat? What is specific heat?
What is specific heat? In this context, for the gas, we have two types. But in general, it's basically a measure of how many joules or how much energy is needed to raise the temperature of a certain quantity by let's say 1 degree Celsius. It's a measure of how easy or difficult to raise the temperature. So in the context of gas, it's the number of joules per mole per Kelvin needed to raise the temperature by 1 Kelvin. Yeah. That's that? Yeah. That's that. So that's on this side. Okay. Yeah, so here is the question. I wrote it earlier. You have air in a container there, and somebody is going to crush that container. It's going to compress the air quickly. So the process will be adiabatic. The process is going to be adiabatic. You're going to crush the container. The initial volume is 500 cubic centimeters. The final volume is going to be 50. Not to scale the drawing. It's going to be a tenth, right? You crushed it, it became a tenth. The initial pressure is 1 atmosphere, and the initial temperature is 30 degrees Celsius. And the question is, what would be the final pressure and volume? I'm sorry, the final pressure and temperature. And then how much work was done on the gas to compress it? So before I continue, will the work done on the gas, in this case, be positive, negative, or zero? Positive. We crushed it, we compressed it. Good. How about the work done by the gas? Negative. It's going to be negative. Yeah, the gas was compressed. Good. So how are we going to find P final, and the work done on it? And I mentioned here it's adiabatic. What happens in an adiabatic process, usually it happens very quickly. So quick that there was no time for the heat to leave or enter the system. Right? Let's say it happened within a millisecond. Heat that entered or left the system is very little, so we can consider it as no heat entered or left. So it's an adiabatic process. It's not a slow process. Or maybe it's perfectly insulated, like a cup of coffee here. Maybe it's perfectly insulated, no heat enters or leaves, so it stays hot for a while. So in this case, somebody crushed it really quick. And in fact, that's what we're going to do in the lab. I already mentioned it will be diatomic gas, air. Okay, so how do I find final pressure? Yeah, can you use the ideal gas law in this case? You could write down the ideal gas law. The problem is you would be missing. You have two unknowns: P final and T final, right? So you won't get too far.